Welcome to ATMOS 5000, Day 8. Our objectives for today are being pulled from Chapter 3, Section 3.5 of the Stull textbook. We're going to focus in on energy transfer mechanisms, basically comparing and contrasting radiation, conduction, and convection. We'll talk a little bit about the advection of temperature, and we will have a small introduction to turbulence. This is just a brief overview of the energy transfer mechanisms that we're going to talk about in more detail shortly. The three energy transfer mechanisms are radiation, conduction, and convection. Radiation is simply the transfer of energy by electromagnetic waves, and an example of this would be the energy that we receive from the sun. Conduction is the transfer of energy through direct physical contact. An example of this would be sitting in the snow and getting cold, energy transfer away from your body. And the last one is convection, which is the transfer of energy by organized fluid motions. An example of this would be cooking macaroni on the stove. You can see the macaroni rise in the middle and sink towards the edge, and you have these large eddies inside the pot of boiling water. Radiation is defined as the transfer of energy through electromagnetic waves. And one of the defining characteristics of this radiation is that it does not require a medium to pass through. It can pass through the vacuum of space. In this example, we have a pot of boiling water, which is quite warm. And if we take our hand and move it close to, but do not touch the pot, we will be able to feel that warmth. Well, the reason we're feeling that warmth is because we have the transfer of infrared heat energy from the pot to our hand through electromagnetic waves. The same principle applies if you happen to be sitting next to a campfire. Hopefully you don't have your feet in the campfire, but you still feel warm. And what's happening is that fire is giving off infrared heat energy, which you're absorbing and feeling warm because of that. Conduction, by contrast, is the transfer of heat energy through direct physical contact. So in this example, we have this pot which is sitting on a hot plate, and the direct physical contact between that hot plate and the pot is transferring energy from the hot surface towards the cold surface. Now, not all objects or substances are good at transferring energy through this mechanism. Examples of good conductors are metal, water, and snow. And objects which are really poor at transferring energy through conduction, examples are air, wood, glass, and foam insulation. And these poor conductors we actually refer to as insulators. So back to our campfire example, if you wanted to cook your hot dog, by conduction, you would actually have to stick your hot dog directly in the flames, and it would be in direct contact with the fire. Convection is the third energy transfer mechanism, and it's the transfer of energy through fluid motions. And in this boiling pot example, we have water that is rising, being heated at the bottom and causing it to boil, and it will be overturning. You'll have rising motion in the center and sinking motion on the outside. The exact same thing is happening in the atmosphere. We have the sun that heats the surface warms up, it then warms the air immediately above the surface through the process of conduction. The hot air is more buoyant than the surroundings, and it will start to rise. As it's rising, it is essentially undergoing convection. Now, sometimes we can see this convection or evidence of this convection when a cloud forms on the top of one of these rising thermals. The reason that happens is because the air has been lifted to the lifting condensation level. However, these rising thermals are often invisible because they're not topped by a cloud, even though they're present in the atmosphere. The other thing which you can't see as part of this convection is the competing or the downward subsidence that's occurring outside of the air that is rising. So you have this loop, essentially, of fluid that's rising in one location and sinking in another, transferring heat energy away from the surface through the process of convection. Temperature advection here, we are referring about the horizontal advection of temperature. So temperature advection is defined as delta temperature over delta time. And mathematically, it's equal to minus U, which is the east-west component of the wind, times the delta T over delta X, which is the temperature gradient in the east-west direction, minus V, which is the wind velocity in the north-south direction, times the temperature gradient in the north-south direction, delta T, delta V. And so the temperature advection depends both on the strength of the wind, that would be the U and the V components, and the angle of the wind relative to the isotherms, basically the strength of the temperature gradients as well. So in figure A, we have wind from the south, where temperature is decreasing from the south to the north. And in this case, the southerly winds are bringing warmer air to a given site. In figure, we refer to that as warm advection. In figure B, we have weaker winds that are still bringing warm air from the south to a given thing, and that would be weak warm advection. And in figure C, the wind is blowing parallel to the isotherms, and so there is no temperature advection in this case. The strongest advection, temperature advection, occurs when the winds are oriented perpendicular to the isotherms, and no advection occurs if the winds are parallel to the isotherms in this case. Turbulence is occurring throughout the atmosphere. Turbulence is basically small and large eddies that are constantly mixing the atmosphere. These eddies range in size from millimeter scale all the way up to kilometer scale. And these eddies mix and blend the atmosphere into a more uniform mixture. And the mixing rate depends upon the strength of the turbulence. The stronger the turbulence, the faster the mixing. And in the atmosphere, the turbulence is typically greatest in the boundary layer near the surface. Why is that the case? Well, that's where we have the greatest friction. With the atmosphere, we have a wind shear near the lowest part of the atmosphere to help create turbulence. We have flow around objects, which create turbulence. And we have heat exchange, but sensible heat exchange between the surface and the atmosphere through radiation and conduction. And all of those lead to a turbulent boundary layer, and that changes throughout the day. There's more turbulence in the afternoon and less turbulence at night.